Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square ABCD. We know that one side of square ABCD equals to 8 units, and inside square ABCD we have two circles. The radius of this big circle equals to 2r, and the radius of this small circle equals to r, and we want to find out the value of r. Okay, before I will answer to the question, I will present to you two new rules. Okay, so the first rule number one, is that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So I read rule number one again. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number one? The meaning of rule number one is that if you have a circle, and suppose that the center of this circle is at this point O, and you also have a tangent to this circle, tangent AB is tangent to this circle at this point. We will define this point as point M. So if you have a radius of this circle that is drawn to the point of tangency, this is the radius of this circle. I will define it as r. So this radius of this circle is drawn to the point of tangency. The point of tangency is point M, so this radius is drawn to the point of tangency. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So whenever you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to this radius. So here we have this radius OM, it is drawn to the point of tangency. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle is 90 degrees. Okay? So, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. When you have a tangent to a circle, that tangent actually creates a point of tangency. The touching point between the tangent and the circle is defined as the point of tangency. Like here, the touching point between tangent AB and this circle is at point M. Therefore, point M is also defined as the point of tangency. And we have the radius of this circle, OM, that is drawn to the point of tangency. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle is also 90 degrees. Okay? So that is rule number 1. I present to you also the second rule, rule number 2. Rule number 2 states that if from one external point two tangents drawn to a circle, then they have equal lengths. I will read rule number 2 again. Rule number 2 says that if from one external point two tangents are drawn to a circle, if from one external point two tangents are drawn to a circle, then they have equal lengths. Okay? Again, if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? Rule number 2 states that if you have this circle and you have an external point of this circle, this point we define it as point P. This point P is an external point of this circle. Why it is an external point of this circle? Because of the fact that point P is not located inside this circle nor on this circle, therefore, but it is located outside this circle. Therefore, point P is defined as external point of this circle. So if from external point P you draw two tangents to this circle, so this is the first tangent, we define the touching point between the first tangent and the circle as point A, and we will draw the second tangent to this circle from point P, and we will define the touching point between the second tangent to this circle as point B. So according to rule number 2, if from the external point P you draw two tangents to a circle, then the lengths of those two tangents will be equal to each other. So what is the length of this first tangent? The length of this first tangent is PA. And what is the length of this second tangent to the circle? The length of this second tangent to the circle is PB. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. So whenever you draw from an external point of a circle two tangents to that circle, then the lengths of those two tangents will be equal to each other. Okay? I repeat again. If from one external point two tangents are drawn to a circle, then they have equal lengths. if you draw from an external point of a circle two tangents to that circle, then the length of those two tangents are equal to each other. That is to say, PA equals to PB. So that is the meaning of rule number 2. So in the next step, we will define the center of this small circle as point P, and we will also define the center of this big circle as point Q. And actually here we will define the touching point between tangent BC and this small circle will be defined as point E. And as you can see, according to rule number 1, this radius is drawn to the point of tangency, that is to say point E. Therefore, the tangent BC will be perpendicular to this radius, that is to say this angle equals to 90 degrees. And this angle also equals to 90 degrees. Okay, and also we know that all 4 angles inside the square are right angles, therefore angle ABC, this angle is equal to 90 degrees, it is a right angle. And we will, in the next step, we will connect together points A, P and A by a straight line. We will define the touching point between tangent AB and this small circle as point F. Then we will join together points P and F by a straight line. Actually, PF is the radius of this small circle because of the fact that line segment PF starts from the center of this circle, that is to say from point P, and ends at point F, that is a point on the circle itself. Therefore, PF is the radius of this circle. So it equals to R. And we also know that this radius, PF, that is the radius of this circle, is drawn to the point of tangency, that is to say, is drawn to point F. Therefore, the tangent AB is perpendicular to this radius according to rule number 1. That is to say, this angle is 90 degrees, and this angle also equals to 90 degrees. Okay? And we will define the touching point. First of all, we will define this point as point G. And we will define the touching point between tangent AD and this small circle as point H. Then we will join together points P and H by a straight line. PH is the radius of this small circle because it starts from the center of the circle. Line segment PH starts from point P, that is the center of this circle, and ends at point H, and ends at point H, that is a point on the circle itself. Therefore, PH is the radius of this small circle, so it equals to R. Okay? And we have also rule number 1 that this radius is drawn to the point of tangency, that is to say point H. Therefore, the tangent AD is perpendicular to this radius, that is to say this angle equals to 90 degrees, it is a right angle, and this angle also equals to 90 degrees, that is to say it is a right angle. Okay? In the next step, we will prove that those two right angles congruent to each other. So we will focus on the right triangle APF. And the right triangle APH. I will repeat again. We will prove that the right triangle APF is congruent to the right triangle APH. So first of all, we know that AF equals to AH according to rule number 2. AF equals to AH according to rule number 2. AF equals to AH according to rule number 2. Why AF equals to AF equals to AH? Because according to rule number 2, from external point A, we have two tangents to this small circle, tangent AF and tangent AH. So, and according to rule number 2, whenever you draw two tangents from an external point to a circle, then the lengths of those two tangents are equal to each other. The length of this first tangent is AF and the length of this second tangent is AH. So according to rule number 2, AF equals to AH. Very simple. And we also know that PF equals to HP. PF equals to HP equals to the radius of this small circle, that is to say 2R. PF equals to HP equals to the radius of the small circle, that is R. And we also have here a common side. PA is a common side, it belongs to both triangles. So I can write down that PA equals to PA. It's a common side that belongs to both triangles. Again, PA equals to PA is a common side that belongs to both triangles. We actually proved that all three sides, 1, 2, 3, of the right triangle APF are correspondingly equal to all the three sides of the right triangle APH. Okay, therefore we actually proved that the right triangle APF can congruent to the right triangle APH according to side rule. So I will write it down. The right triangle APF congruent to the right triangle APH. This is the sign of congruent. So the right triangle APF congruent to the right triangle APH according to side rule. So what is side rule? Side rule says that if you prove that all three sides of one triangle are corresponding equal to all the three sides of the other triangle, then you prove that those two triangles can go into each other according to side rule. So from the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other, that is to say, angle PAF, this angle is equal to angle PAH. Angle PAF equals to angle PAH according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles will be also equal to each other. Those two corresponding angles will be equal to each other. And if we define angle PAF, this angle is alpha, then angle PAH will be also equal to alpha because of the fact that those two angles are equal to alpha. So if this angle is alpha, this angle will be also alpha. So we actually found out that angle PAF equals to angle PAH, and both angles are equal to alpha according to our definition. Okay? In the next step, we will focus on quadrilateral, the small quadrilateral PEFB, this quadrilateral. So in quadrilateral PEFB, okay, we'll focus on quadrilateral PEFB. In quadrilateral PEFB, this quadrilateral, we have three right angles, 1, 2, and 3. So the sum of three right angles is 3 times 90 is 270 degrees. And we will define the fourth angle of quadrilateral PEFB as angle Z. And we actually have a rule that states that in any quadrilateral, the sum of the angles equals to 360 degrees. So according to the rule that I mentioned, the sum of three angles of quadrilateral PEFB, that is 270 degrees, plus the size of the fourth angle must be equal to 360 degrees. Okay, so we will subtract 270 degrees from this equality. We will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that angle Z equals to 90 degrees. It is a right angle. So actually, quadrilateral PEFB, this quadrilateral has four right angles. And any quadrilateral that has four right angles, it must be at least a rectangle. If not a square, it must be at least a rectangle. So I write down that quadrilateral PEFB must be at least a rectangle. Okay, quadrilateral PEFB must be at least a rectangle because of the fact that it has four right angles. Okay, but we also know that the opposite sides of a rectangle are equal to each other. Okay, the opposite sides of a rectangle PEFB must be also equal to each other. That is to say, PE, that is opposite to FB, must be equal to it. PE must be equal to side FB. That are two opposite sides that must be equal to each other according to the rule that I mentioned. PE equals to FB. PE equals to FB according to the rule that the opposite sides of a rectangle are equal to each other. But we know that PE equals to R. PE equals to R, and from this equality we will conclude that FB also equals to R. Okay, FB also equals to R. FB also equals to R. Likewise, side PF equals to EB is two opposite sides in rectangle PEFB. PF equals to EB. PF equals to EB is two opposite sides that are equal to each other in rectangle PEFB. PE equals to FB, but we know that PF, it is PF, sorry, it is PF, yes, PF equals to FB, PF equals to EB, those two opposite sides are equal to each other, but we know that PF equals to R, PF equals to R, and from this equality we will conclude that EB also equals to R. EB equals to R. So here EB equals to R. So actually we found out that quadrilateral PEFB is even more than a rectangle. It is actually a square. Okay. And if opposite sides in a rectangle are equal to each other, let alone the opposite sides of a square are equal to each other, because all sides of the square, all four sides of a square are equal to each other. Okay? So in the next step, that we will find out the size of line segment AF. Okay, let's find out the size of line segment AF. AF, we know first of all that AB equals to 8 units. It is given us the question. Actually all the sides of square ABCD equals to 8 units. So here we can write down that AB equals to 8 units, and we also know that FB equals to R, the radius of this small circle. So what is the size of AF? AF, as you can see from the drawing, equals exactly to AB minus FB. Very simple. AB minus FB equals to AF. AF equals to AB minus FB. From the drawing you can see it clearly that AF equals to AB minus FB, but AB equals to 8 units and FB equals to R. So we found out actually that AF equals to 8 minus R. I will repeat again. AF equals to AB minus FB according to the drawing, but AB equals to 8 and FB equals to R. So in total we found out that AB equals to 8 minus R. So I will write here in the drawing that AB equals to 8 minus R. AB equals to 8 minus R. Okay? And here we have, and we will define the touching point between tangent DA to this big circle as point K or as point O. And as you can see from the drawing, the radius QO, this radius is drawn to the point of tangency, that is to say, the radius is drawn to point O, that is the point of tangency. Therefore, according to rule number 1, the tangent DA is perpendicular to this radius. Okay, so the tangent is perpendicular to this radius, that is to say, this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. And we also know that all four angles inside the square are right angles. Therefore, this angle is a right angle. It equals to 90 degrees. We will define the touching point between tangent DC and this big circle as point K. Then we join together points Q and K by a straight line. Actually, QK, line segment QK is the radius of this big circle because of the fact that line segment QK starts from the center of the circle and ends at point K, that is the point of the circle itself. Therefore, QK is the radius of this big circle that equals to 2r, and that is actually the definition of a radius. Any line segment that starts from the center of the circle and ends at any point on the circle itself, it is defined as the radius. Okay, so QK is the radius of this circle, and again we have this radius QK that is drawn to the point of tangency, that is to say to point K. Therefore, according to rule number 1, the tangent DC is perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, so we will focus on quadrilateral DKOQ. We will focus on quadrilateral DKAQ, this quadrilateral, and we will repeat exactly on the same thing that we did in quadrilateral PEFP. We will do in quadrilateral DKOQ. Okay. Actually, in quadrilateral DKOQ, we have three right angles. The sum of three right angles is equal to 270 degrees. And this angle will be defined as angle Z. And we know that the sum of the angles in any quadrilateral equals to 360 degrees. That is to say, the sum of three angles inside quadrilateral DKOQ that equals to 270 degrees plus the size of the fourth angle, that is angle Z, must be equal to 360 degrees. Again, we will subtract 270 degrees from this equality and we will get that angle Z equals to 90 degrees. So this angle is a right angle, it equals to 90 degrees. So quadrilateral DKOQ has four right angles, therefore it must be at least a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say QO equals to AD. QO equals to AD, but we know that QO equals to 2R, so the AD must be also equal to 2R because of the fact that those two sides are equal to each other. Likewise, we know that KQ must be equal to DO because the opposite sides in a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other, therefore QK equals to DO. Or AQ equals to DO. but AQ equals to 2R, so DO must be equal to 2R because of the fact that DO equals to AQ. So we found out that quadrilateral DAOQ is not a rectangle but a square. Okay, we'll find out the size of line segment OA. Okay, we know that DA, side DA of square ABCD equals to 8 units. And we also know that DO equals to 2R, the radius of the big circle. So OA or AO, OA, from the drawing we can see that OA equals to DA minus DO. Again, DA minus DO equals to OA. DA minus DO equals to DA. DA minus DO equals to OA. You can see it from the drawing. OA equals to DA minus DO. But we know that DA equals to 8 units. We also know that DO equals to 2R. So in total we found out that OA equals to 8 minus 2R. OA equals to 8 minus 2R. Because it is 8, DA is 8, and DO is also 8 minus 2R is exactly OA. Okay. In the next step, we will connect together points Q and A by a straight line. We will define the tangent point between tangent AG and the big circle as point S. Then we join together points Q and S by a straight line. Actually, QS is the radius of this big circle because of the fact that line segment QS starts from the center of this point, that is to say, it starts from the center of this circle, that is to say, from point Q, and ends at point S, that is a point on the circle itself. Therefore, QS is the radius of this big circle, that is to say, it equals to 2R. And again, we have this radius QS that is drawn to the point of tangency. Therefore, according to rule number 1, the tangent AG is perpendicular to this radius, that is to say, this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. Okay, so in the next step we will prove that those two right angles can go into each other. So we actually will focus on triangle AQS and triangle AQO. I will repeat again. We will prove that the right triangle AQS is congruent to the right triangle AQO. First of all, we know that AS equals to AO according to rule number 2. AS equals to AO according to rule number 2. AS equals to AO according to rule number 2. We have explained why they are equal to each other. we have the external point A, and from external point A, we have actually two tangents to the big circle, tangent AS and tangent AO. And according to rule number 2, whenever you draw two tangents from an external point of a circle to that circle, then the lengths of those two tangents will be equal to each other. The length of the first tangent is AS, and the length of the second tangent is AO. That is to say, AS equals to AO according to rule number 2. And we also know that QS equals to QO equals to the radius of this big circle. Okay, QS equals to QO equals to the radius of the big circle. QS equals to QO equals to the radius of the big circle. And we also have here a common side. AQ is a common side that belongs to both triangles. So AQ equals to AQ is a common side that belongs to both triangles. Okay, AQ equals to AQ as a common side. We actually proved that all three sides, 1, 2, 3, of the right triangle AQS are correspondingly equal to all the three sides of triangle AQS. Therefore, we proved that those two right triangles can go into each other according to side rule. So I write it down. I actually proved that the right triangle AQS congruent. This is the sign of congruent, as I already said, to the right triangle AQO, according to side rule. Okay. So from the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles, those two corresponding angles will be equal to each other. So actually angle QAS, this angle, will be equal to angle OAQ. Again, angle QAS will be equal to angle OAQ. And if we define angle QAS, this angle, is better than angle OAQ, this angle will be also equal to beta because of the fact that those two angles are equal to each other. So we actually found out that angle QAS equals to angle OAQ, and both angles are equal to beta according to our definition. Okay? So we know that all the angles inside the square are right angles, they are equal to 90 degrees, and so angle DAB inside square ABCD will be equal to 90 degrees. And DAB equals to 90 degrees, that is from one side, angle DAB equals to 90 degrees, okay? But from the other side, angle DAB consists of four angles. Angle DAB consists of four angles, alpha, and beta. So angle DAB equals also to alpha plus 2 beta. Okay, so from this equality we will conclude that 2 alpha plus 2 beta equals to 90 degrees. This will be equation number 1. Here we will divide equation number 1 by 2 and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. So we found out in equation number 1 that alpha plus beta equals to 45 degrees. But if alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Very simple. Okay? Tangent alpha plus beta will be equal to tangent 45 degrees. So tangent alpha plus beta equals to tangent 45 degrees. It is actually 1. So we got in equation number 1 that tangent alpha plus beta equals to 1. Actually we have trigonometric identity for the value of tangent alpha plus beta. The following trigonometric identity is for the value of tangent alpha plus beta. Actually tangent alpha plus beta equals to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay, so actually we can substitute the value of tangent alpha plus beta. We can substitute tangent alpha plus beta in equation number 1 by this value that equals to tangent alpha plus beta. So we will do it now. So equation number 1 will be, instead of tangent alpha plus beta, we will write down this expression that equals to tangent alpha plus beta. This is actually tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. So, and according to equation number 1, it equals to 1. Tangent alpha plus beta equals to 1. So I will repeat again. So we substitute the tangent alpha plus beta in equation number 1. This equation by this expression that equals to tangent alpha plus beta according to this trigonometric identity. Okay, so in the next step we will calculate the values of tangent alpha and tangent beta from the drawing, and then we will substitute tangent alpha and tangent beta by the values that we found for tangent alpha and tangent beta. Okay, so we will focus on the right triangle APF, on the right triangle APF, on the right triangle APF, tangent alpha will be equal to PF over AF. Okay, tangent alpha equals, in the right triangle APF, tangent alpha equals to PF over AF. But what is the value of PF? From the drawing you can see that the value of PF is the radius of the small circle equals to R, and AF, as you can see from the drawing, AF equals to 8 minus R. So in total we found out that tangent alpha equals to R over 8 minus R. repeat again, we found out that tangent alpha equals to r over 8 minus r. So in the next step we will focus on the right triangle AQO. In order to find out the value of tangent beta. We will focus on this right triangle in order to find out the value of tangent beta. Okay? So if we look on this right triangle, tangent beta equals to QO over AO. According from the right triangle AQO, we can see that tangent beta equals to QO over AO. But what is the value of QO? The value of QO equals to 2R, and the value of AO equals to 8 minus 2R. So actually, in total, we found out that tangent beta equals to 2R over 8 minus 2R. So we actually found out the values of tangent alpha and tangent beta. So in the next step, we will substitute tangent alpha and tangent beta in this equation number 1 by the values that we found out for tangent alpha and tangent beta here. Okay, so actually we will get here that tangent alpha, we found out that tangent alpha equals to r over 8 minus r plus tangent beta. We already found out that tangent beta equals to 2r over 8 minus 2r. So here we must divide it by 1 minus tangent alpha times tangent beta. So tangent alpha is r minus r over 8 minus r, and tangent beta is 2r over 8 minus 2r. And on this side equals to 1. Okay. Again, we substituted tangent alpha and tangent beta in this equation number 1 by the values for tangent alpha and tangent beta that we have already found out, and we got this equation number 1. We have here one equation with one variable only, that is the r, the radius of the small circle. So we will find the common factor. We will take out a common factor for this two expressions, and we will take a common factor for one in this expression. Okay. So here a common factor for these two expressions will be 8 minus r times 8 minus 2r. So here we have r. So we must multiply r by 8 minus 2r in order to get this expression. And here we have 2r. So we must multiply 2r by 8 minus r in order to get this expression. Then we will divide all by 1. So here we will substitute 1 by 8 minus r over 8 minus r. 8 minus r over 8 minus r is 1. And we will multiply it by 8 minus 2r over 8 minus 2r. That is actually also 1. And 1 times 1 is 1. So this expression equals to 1. And we have to substitute also this expression. So here we will substitute it by minus r times 2r is minus 2r squared. Okay? So actually here we have in the numerator 8 minus 2r, 8 minus r times 8 minus 2r, and we have in the denominator the same expression, 8 minus r times 8 minus 2r. So those two expressions will get cancelled because of the fact that when we will divide those two expressions one by the other, it will be equal to 1. That is to say, it actually get cancelled. So what is left after we cancel those two expressions? What is left is actually that r 8 minus 2r plus 2r 8 minus r, and in the denominator we will have 8 minus r times 8 minus 2r minus 2r squared equals to 1. So actually that is what we got after we cancelled those two expressions. Here we will cross multiply this expression and we will get that r 8 minus 2r plus 2r 8 minus r equals to 8 minus r times 8 minus 2r minus 2r squared. So actually we got this expression after we cross multiplied this expression. Now we will open the brackets on this equation number 1, and we will get that r times 8 is 8r, r times minus 2r is minus 2r squared, plus 2r times 8 is 16r, 2r times minus r is minus 2r squared, equals to 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, minus r times minus 2r is plus 2r squared, minus 2r squared. Here we have plus 2r squared, minus 2r squared is 0, so those two expressions will get cancelled. So what is left after we cancelled those two expressions? Those two expressions is actually, here we have 8r plus 16r is 24r, minus 2r squared is minus 4r squared, all equals to 64, minus 16r minus 8r is minus 24r. So here we will subtract 24r from this equation number 1, and we will get that minus 4r squared equals to 64 minus 48r. So here we will add to this quadratic equation 4r squared, and we will get that r squared minus 48r plus 64 equals to 0. So we will divide this quadratic equation by 4 and we will get that r squared minus 12r plus 16 equals to 0. We have here a quadratic equation, and the general formula for a quadratic equation is actually ax squared plus bx plus c equals to 0, when a, b, and c in this general quadratic equation are the coefficients of this quadratic equation, and x is the variable that we are looking for, and we can find the value or the values of x according to the following formula for x. X actually equals to minus b plus minus root of b squared minus 4ac over 2a here. A, b, and c are the coefficients of this general quadratic equation, and x is the variable that we are looking for. So in our specific quadratic equation, the variable x is actually r. So x equals to r. R is the variable that we are looking for, the radius of the small circle, and the coefficients a, b, and c in our quadratic specific quadratic equation are as follows: a equals to 1, b equals to minus 12, and c equals to 16. So we will put this data inside this equation in order to find out the value or the values of r, the radius of the small circle. X equals to r, so r equals to minus b, b equals to minus 12, so minus minus 12 is 12, plus minus root of b squared, b is minus 12, so minus 12 squared is 144, minus 4 times a is 1, 4 times 1 is 4, so it is minus 4 times 16 is minus 64 over 2 times a is 1, so 2 times 1 is 2. So we got that r equals to 12 plus minus the root of 144 minus 64 is 80 over 2. So here we have 80 inside the root. 80 is 4 times 20, so I'll write it down that r equals to 12 plus minus 4 times 20, that is 80, over 2. We know that the root of 4 is 2, so I'll write it down. R equals to 12 plus minus 2. Inside the root we left only with 20 over 2. Okay, so the radius of the small circle equals to 12 over 2 is 6 and 2 over 2 is 1. So it is plus minus root 20, but 20 equals to 4 times 5. 4 times 5. So the radius of the small circle equals to 6 plus minus. The root of 4 is 2, and inside the root we left only with 5. So we have two solutions to the quadratic equation. The first solution is that the radius of the small circle R equals to 6 plus 2 times root 5 units. And the second solution is that the radius of the small circle equals to 6 minus 2 times root 5 units. So we have those two solutions for R, but we know that the size of one side of square ABCD is 8 units. As you can see, AB equals to 8. And as you can see from the drawing, the small circle is located inside the square. So if the small circle is located inside the square, the radius of the small circle must be less than the size of AB. Otherwise, it will not be located totally inside the square. So R, the radius of the small circle, must be less than 8 units because it is totally located inside the square. But this answer that R equals to 6, this solution that R equals to 6 plus 2 root 5 is greater than 8 units. And it is impossible that the radius of this small circle will be greater than 8 units because it is located totally inside the square. So the radius can never be greater than 8 units. So the radius, the solution that R equals to 6 plus 2 times root 5 that is greater than 8 units is not correct answer. We will cancel this option. And the only solution that is left is that the radius of the small circle equals to 6 minus 2 times root 5 units, or in terms of numbers, the radius of the small circle equals to 1.53 units. Okay? So I repeat again, we found out that the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we know that we have square ABCD. One side of square ABCD equals to 8 units, and inside the square we have two circles. The radius of this big circle equals to 2r, while the radius of this small circle equals to r, and we want to find out the value of r, or the size of the radius of this small circle. Okay. So before I solve the question, I presented to you two new rules. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. A tangent to a circle is perpendicular to the radius drawn to its point of tangency. What is the meaning of rule number 1? Rule number 1 states that if we have a tangent to this circle, actually the tangent AB to this circle touches the circle at point M, or the touching point between tangent AB to this circle is at point M, and point M is defined as the point of tangency. Point M is defined as the point of tangency, and when we have a radius that is drawn to the point of tangency, that is to say to point M, then the tangent AB will be perpendicular to this radius. That is to say, this angle is 90 degrees, and this angle is also equal to 90 degrees. Again, whenever the radius is drawn to the point of tangency, then the tangent will be perpendicular to that radius. So in this example, if this angle is 90 degrees, this angle is also 90 degrees because of the fact that the radius is drawn to the point of tangency. Therefore, the tangent is perpendicular to this radius. This angle is 90 degrees, and this angle is also equals to 90 degrees. So this is rule number 1, and I presented to you also rule number 2. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. I repeat again, if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? Rule number 2 states that if we have a circle at external point, this external point, and I repeat again that the reason that P is external point of this circle because point P is not located inside this circle nor on this circle, but is located outside the circle. That is the reason that is defined as external point of this circle. Okay, so point P is external point of this circle, and if from point P you draw two tangents to this circle, that is to say tangent PA and tangent PB, then the lengths of those two tangents are equal to each other. The length of this first tangent is PA, and the length of the second tangent is PB. And according to rule number 2, the lengths are equal to each other. That is to say, PA equals to PB. So whenever you draw two tangents to a circle from an external point of this circle, then the lengths of those two tangents will be equal to each other. In this example, we have external point P, and from external point P we draw two tangents to this circle, and therefore according to rule number 2, the lengths of those two tangents will be equal to each other. That is to say, PA equals to PB. Okay, so that is rule number 2. Then we actually define the center of this small circle as point P, and we define the center of this big circle as point Q. Then we join together points A and P by a straight line. We join together points P and F by a straight line. Actually, point F is the point of tangency of tangent AB to the small circle. Again, point F is the point of tangency of tangent AB. Tangent AB is tangent to the circle, to the small circle at point F. Therefore, point F is the point of tangency. Okay, and we see here in the drawing that the radius PF is drawn to the point of tangency, that is to say point F. Therefore, the tangent AB is perpendicular to this radius. That is to say, if this angle is 90 degrees, and this angle is 90 degrees because of the fact that the tangent AB is perpendicular to this radius. So this angle is 90 degrees, and this angle is also 90 degrees. And we also know that tangent AG is perpendicular to this small circle at point H. Therefore, point H is defined as the point of tangency. And we have radius PH that is tangent, that is drawn to the point of tangency, that is to say to point H. Therefore, the tangent AZ is perpendicular to this radius, that is to say this angle is equal to 90 degrees, and this angle also equals to 90 degrees. And the same thing is true also here. We have this radius that is drawn to the point of tangency, that is to say point E. Why point E is a point of tangency? Because of the fact that tangent BC is tangent to this circle at point E. Therefore, point E is defined as the point of tangency. and this radius PE, is drawn to the point of tendency. Therefore, according to rule number 1, the tangent BC is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle is also 90 degrees. Okay? And the same thing is true here. We have this radius that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees and this angle also equals to 90 degrees. We have also here QK is the radius of this big circle, and we have this radius that is drawn to the point of tendency, that is to say to point K. Therefore, this angle is 90 degrees and this angle is also equals to 90 degrees. Okay, so in the next step we will proved that those two right triangles can congruent to each other. Why? Because we know that AF equals to AH according to rule number 2, because from the external point A we have two tangents to this circle, tangent AF and tangent AH, and according to rule number 2, if from an external point you draw two tangents to a circle, then they will be equal to each other. So tangent AF is equal to tangent AH according to rule number 2. And we also know that those two radiuses are line segment PF equals to line segment PH, because of the fact that there are the two radiuses of this small circle, and we have also the common side. PA is a common side, it belongs to both triangles, so PA equals to PA as a common side. So we actually proved that the right triangle APF is congruent to the right triangle APH according to side rule. So what is side rule? Side rule is that if you prove that all the sides of one triangle are corresponding equal to all the sides of the other triangle, then you prove that those two triangles can go into each other according to side rule. So from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So that is to say, angle PAF equals to angle PAH. And if this angle is alpha, then this angle will be also equal to alpha, because of the fact that those two angles are equal to each other. So we found that angle PAF equals to angle PAH, and those two angles are equal to alpha according to our definition. Okay? And then we focused on the quadrilateral PAFB. On quadrilateral PAFB, we have three right angles, and the sum of the three right angles is 270 degrees. And we define this angle as angle Z, and we have the rule that the sum of the angles in any quadrilateral equals to 360 degrees. So the sum of the three angles, that is 270 degrees, plus the size of the fourth angle, that is Z, must be equal to 360 degrees according to the rule that I mentioned. We substituted 270 degrees from this equality, and we got that angle Z equals to 90 degrees. Angle Z equals to 90 degrees, this angle equals to 90 degrees. So we found out that all the angles inside quadrilateral PEFB are right angles. Therefore, quadrilateral PEFB must be at least a rectangle, if not a square. Why? Because of the fact that it has four right angles. Okay, so quadrilateral FEB must be at least a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite side FB equals to the opposite side PE in rectangle PEFB. PE equals to FB. PE equals to FB, but we know that PE equals to R. PE equals to FB, but we know that PE equals to R. So from this equality we will conclude that PB equals also to R. Okay? PB also equals to R. Okay? we will conclude that PB also equals to R. Actually it is PE equals to FB, and actually PE equals to R, PE equals to R, because of the fact that PE equals to R, PE equals to R, then we will conclude that FB also equals to R. Okay, FB equals to R. So from this equality we will conclude that FB equals to R. Here FB equals to R, and we also know that the opposite side PF equals to the opposite side EB in the rectangle PEFB. Okay, EB equals to PF, PF equals to EB, because the opposite sides of a rectangle are equal to each other, but we know that PF equals to R. PF equals to R, so from this equality we will conclude that BE also equals to R. PE also equals to R, so we found out that all the sides of quadrilateral PEFB are equal to each other, they are equal to R, therefore quadrilateral PEFB is a square. Okay, and then we calculated the value of line segment AF. What is the size of line segment AF? AF equals to AB minus FB. Okay, AF equals to AB minus FB. But we know that AB equals to 8 units and FB equals to R. So in total we found that AF equals to 8 minus R. Okay, AF equals to 8 minus R. Then we focused on the quadrilateral DKOQ is quadrilateral. In this quadrilateral we have 3 right angles, and the sum of these 3 right angles is equal to 270 degrees, and we know that the sum of the angles in any quadrilateral equals to 360 degrees. So actually the sum of the 3 angles in quadrilateral DKOQ is 270 degrees, plus the size of the 4th angle, that is Z, must be equal to 360 degrees. We subtracted 270 degrees from this equality, and we got that angle Z equals to 90 degrees. This angle equals to 90 degrees. So we have 4 right angles inside quadrilateral DKOQ, therefore it must be at least a rectangle. Okay, quadrilateral DKOQ must be at least a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, QO equals to AD, but QO equals to 2R, so DK will be also equal to 2R, and also the opposite side KQ equals to DO, but we know that KQ equals to 2R, so DO will be also equal to 2R because of the fact that they are equal to each other. So we found that all the sides of quadrilateral DKOQ are equal to each other, they are all equal to 2R. Therefore quadrilateral DKOQ is a square. Then we actually proved that those 2 right triangles can go into each other. Actually we know that AS equals to AO. AS equals to AO according to rule number 2. AS equals to AO according to rule number 2 because of the fact that A is an external point in relation to this big circle, and from the external point A we have two tangents to this big circle, tangent AS and tangent AO. So according to rule number 2, they are equal to each other. So AS equals to AO, and we also know that QS equals to OQ equals to 2R. Okay, and we also have a common side. QA is a common side, it belongs to both triangles, so QA equals to QA is a common side, so we actually proved that the right triangle QASQ can congruent to the right triangle AQO according to side rule. Okay, from the fact that those two triangles can congruent to each other, we conclude that those two angles are equal to each other. And if one angle is beta, then the other angle will be also equal to beta because of the fact that they are equal to each other. Okay? So, we know that all the angles inside the square are right angles, therefore angle DAB equals to 90 degrees. From one side angle DAB equals to 90 degrees, but from the other side angle DAB consists of 4 angles. That is to say, angle DAB equals to 2 alpha plus 2 beta. So from the other side, angle DAB equals to 2 alpha plus 2 beta. So from this equality, we conclude that 2 alpha plus 2 beta equals to 90 degrees. We will divide the equation number 1 by 2, and we will get that alpha plus beta equals to 45 degrees. If alpha plus beta equals to 45 degrees, then tangents alpha plus beta will be equal to tangents 45 degrees. But tangents 45 degrees equals to 1. So we got equation number 1 that states that tangents alpha plus beta equals to 1. And we have this trigonometric identity. So according to this trigonometric identity, we can substitute tangents alpha plus beta by this expression. Okay, we substitute the tangents alpha plus beta by that expression. We got this equality. Then we calculated the value of tangents alpha and tangents beta. Here we can see in this right triangle that tangents alpha equals to R over 8 minus R. And from this right triangle, we can see that tangents beta equals to 2R over 8 minus 2R. Okay? So tangents alpha equals to R over 8 minus R, and tangents beta equals to 2R over 8 minus 2R. So we substitute the tangents alpha and tangents beta in this equation number 1 by the values that we found for tangents alpha and tangents beta, and we got this equation. And we've solved this equation, and we found two answers to this equation. The first answer, that R equals to 6 plus 2 times root 5, is not possible because of the fact that the small circle is located inside the square. So the square must be, and the one side of this square equals to 8 units. That is to say that the radius of this small circle must be less than 8 units in order that it could be located inside, totally inside the square. In order that the small circle will be located totally inside the square, the radius of this small circle must be less than 8 units. And but the answer is R equals to 6 plus 2 times root 5 is greater than 8 units, so this answer is not possible, and we left only with the answer that the radius of the small circle equals to 6 minus 2 times root 5 units, or in terms of numbers, the radius of the small circle equals to 1.53 units. Again, the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, thank you very much.